Let's start with a review of the notion of cosets from the last lesson. So, consider the additive group Z12 and its subgroup H containing 0, 4, and 8. How many distinct cosets of H do you expect? Find all of them. And as a starter, here is one such coset, 6 plus H, which we obtain by adding 6 to each element of H. So if you could pause the video and see if you can answer this question. And here are the distinct cosets of H. There are 4 of them, and perhaps we could have predicted that because there are 12 elements in Z12, 3 elements in H, and 12 divided by 3 is 4. Another thing we recall is that the cosets 3 plus H and say 11 plus H are the same, even though the coset representatives 3 and 11 are different as elements of Z12. And in the next slide, we'll review the generalization of how these coset representatives must be related so that the cosets that they generate are the same. But before that, we'll introduce one notation, and that's the index of H in G. And this denotes the number of distinct left cosets of H and G. So we're counting the distinct ones. So for instance, in the example above, the index would be 4 because there are 1, 2, 3, 4 distinct cosets of H. Let's review when 2 cosets are equal. And we'll start with a case when the group operation is addition. Then, the cosets A plus H and B plus H are equal precisely when the difference of the coset representatives, namely A minus B and B minus A, are elements of H. Now let's look at the multiplicative case when the group operation is multiplication. Then the cosets AH and BH are equal precisely when the elements B inverse A and A inverse B are elements of H. And here, please be careful, it's B inverse A and A inverse B, not AB inverse and BA inverse. Now, to remember that we need to consider B inverse A as opposed to AB inverse, and likewise for A inverse B as opposed to BA inverse, here's a quick mnemonic device that we looked at last time. Now, this isn't a proof of this criterion, just a mnemonic device, but I think it's helpful. So AH is equal to BH if and only if, well, let's just multiply both sides on the left by B inverse. Then we get B inverse AH is equal to just H because this B and B inverse cancel. So then we have a coset whose representative is B inverse A. So B inverse AH is equal to the original subgroup H, and that's true, as we saw last time, precisely when B inverse A is an element of H. So once again, this isn't a proof of this particular criterion, but it's a helpful mnemonic device. And I just wanted to review these criteria because we'll be using them in our work in today's lesson. Now please pause the video and work on day 20 classwork. And afterwards, we'll go over some of the problems and concepts. Let's start with problem 1b. If a subgroup H contains 12 elements, then the group G cannot contain 1000 elements because 12 is not a divisor of 1000. And this is really for the same reason why 1000 eggs cannot fit in dozen egg cartons if all those egg cartons are to be completely full. And this example motivates the following theorem, which is perhaps one of the most important theorems in group theory. And it's Lagrange's theorem, which says, let H be a subgroup of a finite group G. Then the number of elements of H must be a divisor of the number of elements of G. And so we will give a proof of this theorem in the next several slides. So once again, here's the statement of Lagrange's theorem. And to motivate the proof, we're going to draw a little picture here. So imagine group G right here. And let's say we have a subgroup H, perhaps this portion of group G is the subgroup H. And because it's a subgroup, it must contain the identity element. And so right here, let's label this as H. And we can think of it as also the coset epsilon H. But maybe that doesn't take up the whole group. So there is an element, let's say A here. That's not an H. But then A can be a coset representative, and the coset that it generates would be AH. So we have the coset AH containing the element A. And maybe that doesn't take up the whole group G. And so now there's, say, an element B that's not in either of our first two cosets, and that generates the coset BH. And so we have our coset BH right here. And then we keep going. Maybe there's an element C here that's not in any of the cosets so far, and then we have our coset CH. And looks like we have one more coset here. Let's say the element D is right there. And we have the coset DH. And so we have 1, 2, 3, 4, 5 distinct cosets of H. And thus we say that the index of H and G is 5, because 5 cosets of H are needed to fill up all of the group G. Now, what does this picture have to do with proving Lagrange's theorem? Well, let's just suppose that our subgroup H has 12 elements. Then we have 12 elements here. This would have 12 elements. BH would have 12 elements. CH would have 12 elements. And DH would have 12 elements. So all in all, group G would have 60 elements. And we see that 12 is indeed a divisor of 60. Now, when we just counted all these elements of G, there are a couple of assumptions that we were making. And in fact, those assumptions will be our proof ingredients. So here they are. Proof ingredient number 1 is that all the cosets of H have the same size, namely the size of the subgroup H. And that was proven in chapter 19, and so please take a look at the chapter 19 reading for that. Now, our focus in today's lesson will be showing that the distinct cosets of H form a partition of G. So that's going to be our focus. And recall that when we say those cosets form a partition of G, what we mean is that they cover all of G and they don't overlap with each other. And if we have those two proof ingredients, that all those cosets have the same size and they form a partition of G, then we can conclude that those two ingredients do in fact prove Lagrange's theorem. And so see if you can make sense of that kind of from an intuitive perspective. And then in the chapter 20 reading, there is a more detailed explanation of why those two proof ingredients do end up proving Lagrange's theorem. So let's go ahead and prove ingredient number 2. Once again, the distinct cosets of H form a partition of G. And we'll start with part A. So we need to show that every element of G is contained in some coset. Well, so what if we're given some arbitrary element A? Is there a coset of H that contains that particular element A? Why, yes. In fact, the coset AH contains the element A. And that's the argument for part A, that given an element A, it is contained in the coset AH, its own coset that it generates. Now let's show the second part of the partition claim, namely that the distinct cosets of H do not overlap with each other. And so what we need to show is that if AH doesn't equal BH, so if we have two different cosets, then they do not overlap. Now we have not equal to, do not overlap. I think this is screaming contrapositive, so that's what we're going to show instead, that if AH and BH do overlap, then they are in fact the same coset. We will give a proof outline of this contrapositive, and I'll leave it up to you to turn that into a complete proof. So let's begin by identifying the hypothesis and the conclusion. And those will give us the first and last steps of our outline. So we'll start by assuming that the cosets AH and BH overlap, and we'll eventually prove that those two cosets are, after all, the same. And so here is a little visual that might be useful. We have the coset AH here in red and BH here in blue. And we know they overlap, which guarantees the existence of an element that's in both cosets. And let's call that element G. And so that's our next step in the outline. Let G be an element that's in both cosets AH and BH. Now that means we know what that element little g has to look like. In particular, because it's in the coset AH, it has to look like A times little h. And likewise, it has to look like B times little k, where little h and little k are both elements of the subgroup H. And now we can say that AH and BK, those two elements must be equal to each other because they're both equal to G. And so that's our next step, that AH is equal to BK. But now I claim that this implies the following. By left multiplying both sides of this by B inverse and right multiplying both sides by H inverse, we obtain that B inverse A is equal to KH inverse. And because H is a subgroup, this product is an element of H. And so what we just showed is that B inverse A is an element of H. And as we reviewed earlier in the lesson, that's a criteria for concluding that the cosets AH and BH are equal. And that's the proof outline of the contrapositive. Now that we've discussed the proof of Lagrange's theorem, let's use it to settle an old conjecture. So here's a motivating question. Say we have a group element with order 12. Then can the original group G contain 1,000 elements? Why or why not? Turns out the answer is no. And the reason will sound familiar. It's because 12 is not a divisor of 1,000. And more specifically, a conjecture that we had made in the past is the following. Let G be a finite group and little g one of its elements, then the order of that element must be a divisor of the number of elements in G. We'll give a proof outline of this conjecture. So we'll start by letting n be the order of element G, and we have to eventually show that n is a divisor of the number of elements in our group. Now, if we're going to use Lagrange's theorem, we need a group, but we also need a subgroup. And what's that subgroup going to be? Well, it's going to be the cyclic subgroup generated by our element little g. And so its elements would be the identity, g to the first, g squared, g to the third, dot, 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 all the way to g to the n minus 1, because g to the n will bring us back to the identity. And that cyclic subgroup, as we can see here, contains n elements. So that's going to be key right there. Now, Lagrange's theorem says that since bracket G is a subgroup of our original group G, then the number of elements in this cyclic subgroup must be a divisor of the number of elements in our whole group. But this is n, which is the order of little g. And therefore we can say that n is a divisor of the number of elements in the group. And that's the proof outline of the conjecture. And that's also the end of this lesson. So I will see you next time.